these questions, you only had to graph 10, 11, and 12. But let's look up for a minute before we get to that and talk about questions like 1, 2, and 3. It says find the domain, points of discontinuity, and x and y intercepts of the rational function. Really, I want to talk about how do you find the domain and range of a rational function. So I'd like to pick one. I'd actually like to do number 3. So if everyone could look at number 3 for me real quick. And let's look at this one. Hang on one second. Let me just write it down. Let's remind ourselves what the steps are when I'm asking you to graph a rational function. Who remembers what the steps are? What's the first step? Shamar, put your head up, baby. Come on. Factor. Good. Sometimes it's already factored. Is this one factored? No. Okay, good. Now, sometimes it's already factored. This one's not already factored. So we do need to do that. Sometimes you have to factor the numerator and the denominator. This one is just the denominator. So if I factor it, if I factor the denominator, what two numbers, Tim, you can help us out here. What two numbers multiply to be negative? Is it negative 8 or positive 8? Negative. It's negative, and this is a positive 2. All right, I was going to say something was wrong. There we go. What two numbers multiply to be negative 8 and add to be 2, Tim? If we're factoring this.
Oh, multiply negative 8 and 4.
Positive 4 and negative 2. Okay, so those are the two numbers that are going to, that's the correct factorization of this problem. April, what's step 2 after I factor? Ask April. Hang on. You factored it. I have to do what, baby? Not rewrite it. Well, what do you mean by that? I'm checking for what? What's step 2? Factor, and then I check for holes. Okay? Is there a hole here? There actually is. Okay? And the hole happens to be, the x plus 4 factor is common both in the numerator and the denominator. That means that there is a hole. So on their OPQ, I'm going to ask you to list the holes, the vertical asymptotes, the horizontal asymptotes, and I'm also going to ask you to write the domain. Okay, we're going to talk about domain and range. So I'm going to have range 2. I don't think on the OPQ I asked for the range, but we'll at least talk about it here. So I have a hole where the factor that canceled out equals 0. Which means the hole is at negative 4. Okay? Are we okay with that? Well, hang on, not yet. We're not there yet. April, you said I have to rewrite it now. Okay, so tell me what it was to rewrite it. What's left on the numerator when it cancels? 1 up there. Perfect. Okay, it should just be a line. Yeah, there we go. All right. I still have a hole, and I'll have to worry about that in the graph in a minute, but we're going to go ahead and simplify our function. Okay. Now, the second step, we factored, we checked for holes. What's the third step, Matthew, in the process? Third step is vertical. Okay, vertical. So we're just kind of going through our steps. How do I check for vertical asymptotes, Joseph? What do I do? How do I take my simplified function and find the vertical asymptote? What equal to 0? The denominator. Okay? So I'm going to take the x minus 2. Sometimes there's more than one thing still down there in factored form. Set each of the factors equal to 0. So the vertical asymptote is at positive 2. Okay? So if I wanted to, I could go ahead and draw in the vertical asymptote at positive 2. I know that's what's going to happen. Now, to figure out what the domain is where these discontinuities happen. Remember how I said a point discontinuity was a hole, and a non-removable discontinuity was an asymptote. So wherever the vertical asymptote and the holes are places where the graph doesn't exist. So we're going to come back to that when I graph it, and I'll show you what I mean, and we'll put together what the domain is. But the domain is related to these holes and asymptotes. These are what are called domain restrictions. All right, step 4, we're looking for the final kind of asymptote, and it's going to be a what kind? Horizontal. And that's where you have to look at the degree of the numerator and the degree of the denominator. Okay? As in a lot of cases that we've already looked at, Which degree is bigger, the top or the bottom? The bottom. And when the bottom is bigger, what's the horizontal asymptote? 0. Good. So I know I'm going to have y equals 0 as my horizontal asymptote. So I'm going to draw that in. Okay? You look at the power. So I'm going to look up here. It's a great question. I'm going to look at the power of this x and the power of this x, the highest power of each. I do. It doesn't really matter because down here the power is still higher, right? But usually it's just safer in case I made a mistake somewhere.
Where does that go?
Wait, so when it says higher on top and lower
If it's higher on the top, there is no horizontal asymptote. Put none.
okay, and then when it's equal to
We're going to look at an equal one. We're going to look at that because we're going to look at number 12, and that's where they're equal. Okay? So hang tight. Say that again. When it's not 0, you mean?
Yeah.
Yeah, that's what we're going to talk about in a minute. Okay. When is the horizontal asymptote not 0? We'll look at that in a couple minutes. That's not this case, but it's when the degrees are the same, and then you just look at the numbers, the leading coefficients in the front. So we'll talk about how to find that in a minute. All right, so in this particular function, I know you weren't asked to graph it, okay? You were just asked to find the domain, but I'm going to graph it too, just to kind of remember what we're doing here. The fifth step and the final step is to use your calculator and to figure out where the pieces go. Sometimes a calculator is helpful, but as Patrick figured out, sometimes it's not, right? So if you look at this problem, we plug it in. We have x plus 4 in the numerator. And in the denominator, we have x squared plus 2x minus 8. And we'll go ahead and get a standard window. We should see a vertical asymptote in the right place. They don't show it, the dotted line doesn't show up, but it does look like it's there. And so if we put our pieces to the graph, it looks something like this. Would you agree? Okay. What haven't I placed on my graph? The whole. Good, Jennifer. Okay? So I'm going to go back and do that. The whole happened when x equals -4. So I'm going to look 1, 2, 3, -4, and I'm going to put a hole on the actual graph itself. Some people feel more comfortable just erasing and going and going back 1, 2, 3, 4 and putting a hole like that so the line doesn't go through it. I don't care. Just show me the hole on the graph. Okay? All right, so we've graphed it. Didn't have to on this one. But what would the domain be? So let's think about it from a graph perspective. If you look at the graph, the domain is where x is, right? From left to right. What can't x be? What are the domain restrictions? Well, x can't be -4 because there's a hole there. There's no part of the graph there. If I keep going, x can't be 2 because there's an asymptote there. So x can be anything except for 2, and x can't be -4. And so that's how you would write the domain. So do me a favor on your papers for homework, underneath number 3, please go ahead and write what the domain is there. Okay? So x can be anything except, so the notation is all x's such that x can't be 2 or for -4. X, just having to write that will be on your OPQ. It's the only, yeah, it's just where the hole and asymptotes are. But just make sure your notation is that x can't be those things. Okay? Doing okay? Let me know. Hole and vertical asymptotes, because those are the domain, those are the restrictions on x. Notice horizontal asymptote dealing with the y. That's a range restriction. Okay? All x's, yep, x/, sometimes there's a colon there, depends on the notation. Now, I don't think the range is on your OPQ, but as Christian was saying, this horizontal asymptote deals with y. Ranges are y's. If I go up and down and I'm looking at y values, what is one y value that can't happen? Well, 0. Would you agree? Okay. There's also a y value here at where the hole is. It's some decimal number. We know for a fact that it can't be 0. But there is another y value somewhere negative something where that value is. But for one of the main restrictions is it can't be 0. Okay? But again, I'm more worried about your domain restrictions right now. Huh?
How do you see 0?
Because it's a horizontal asymptote. Right? So I know for a fact it can't be that.
I'm scared to think it'll be you now.
No, don't be. It's nothing different. It's just adding.
Added stuff.
There's not a lot of added stuff.
Equals 0.
When the degree of the numerator, you wrote it down in your notes. When the top is greater than the bottom, there's no horizontal asymptote. Which is not going to happen, because I'm going to give you one with the horizontal asymptote. Okay? Okay.
Wait, can you hear over?
Okay. When bottom is bigger, y equals 0. I'd like to look at one where the degrees are the same, so we can look at what the horizontal asymptote would be in that case. That's like number 12.
No, it's like number 7.
Let me see it 7 too. 7 also, okay? Both 7 and 12 on your homework have those. So let's look at both of those so you can see what I mean, okay? So this is number 7 and this is number 12. Let's go ahead and just for practice and not graph them, but check for holes, vertical asymptote, horizontal asymptotes, and we'll go ahead and write the domain just for practice. Okay, well you need to. Okay, so we'll do holes, VA, HA, and domain. All right. So, do either of these have holes? Yes or no, and why, Carolina? I heard yes and I heard no. Carolina, why no?
You're wrong.
She's not wrong. Shush it. Yeah, there's no common factor in both the numerator and the denominator. Good on you. Okay? Perfect. So neither of these have holes. So you would literally write none. Okay? Because there's no holes. Okay. Vertical asymptotes. They both have one. Travis, look at the number 7. Tell me where the vertical, how do I find the vertical asymptote in number 7? Shh. I'm listening. You don't know. All right. Then listen, okay? Go ahead.
The bottom number.
What do you mean? What do I do with the denominator?
You gotta equal it to 0.
Good. So x plus 5 equals 0. Solve it. So
Negative 5.
awesome. That is your vertical asymptote.
And the other one gonna be
Well, hang on. Let somebody else do that one. Okay? It's a decimal. I agree. Okay? So again, I'm going to do the same process. I'm going to set the denominator equal to 0. But I have to solve this. Add 1 and divide by 3. So x equals 1/3 is your vertical asymptote. You can have fractional asymptotes. That's okay. You're just going, when you graph it, where would 1/3 be? Between 0 and 1. A little closer to 0, right? But a little bit to the right. So you would just draw that. You would have to estimate it on your graph. Just estimate approximately where 1/3 would be. Maybe, maybe not. They're all different, right? You'd be all right, right? All right, let's look at horizontal asymptotes. This is a special case because we're looking at the degree of the top and the degree of the bottom. If you look at the degree of the top, in both of these cases, the powers are 1. They're the same. So when that happens, your asymptotes are the numbers in the front. So the horizontal asymptote for the number 7, it's y equals 1/1. So y equals 1. Number 12, the horizontal asymptote is going to be 2/3. Perfect. So again, another fraction, but we could graph it between 0 and 1 and closer to 1 this time and estimate where the where the horizontal asymptote is going to be. All right, now I'm not going to graph these, but let's go ahead and just double check the domain. Okay, what am I looking at for domain again? The domain, that's the x restrictions, but am I looking at holes, vertical, or horizontal? Holes and vertical. Good. So let's go ahead and write what the domain would be on number 7. All x's such that what happens? Don't say x equals 5. That would be wrong. There you go. X cannot equal -5. Very good. But I would grade it wrong on the OPQ if you wrote that, right? So just make sure that you're writing what you really mean. All right? How about the domain? All x's such that x cannot equal what? 1/3. Now, there weren't any holes in this case, but double check because on your OPQ there might be, okay? So it would be both holes and vertical relate to your domain. All right, I think you guys got this. Put everything away. You can use your calculators, but don't rely on it 100%, okay? I need your folders up. There are folders underneath the fridge. If you would kindly get those out. Everybody needs their own. And then when we get done, we're going to move on. So I think you're going to find what we do today a little refreshing. It's going to be pretty easy because it's kind of what we've already been doing. It's just we're not going to graph it anymore. Okay, so we're just going to look at just pure algebra, not graphing, and just simplifying these rational expressions. Okay, so we first have to remember what it means to be in simplest form. So if you look at this particular number 1 here, look at these different fractions across the top. Which ones are in simplest form? What does it mean to be in simplest form? Can't reduce it anymore. It's already been reduced as far as possible. So is 2/6 reduced? You can keep going. So it's not in simplest form. How about 3/5? All right. 6/9? Okay. 5/11? Okay. 7/12?
No.
Yes. In other words, we can't simplify it any further. Okay. So exactly, we're looking at prime numbers or not even necessarily have to be prime because 12 is not prime. Right? But the same number can't go in the numerator and the denominator. Okay? Okay. So, could we reduce in this case? 36/54, how does that reduce? Which number in column B matches up with it? What number goes into both 36 and 54?
27. Oh, 36 and 54?
Has to go into both.
7, 6.
I hear 7, 6, and 27. I'm just yelling out numbers.
6.
Okay, shh. Okay. Okay. So what would it reduce to? Well, the good news, if we go ahead on our calculator, we should know how to do this. We know that a common number that goes into both 36 and 54 would be, what's 9 times 6? What's 6 times 6? So doesn't 6 go into both of them, which is what you guys had decided. 36 divided by 6 is 6. And then we can keep going, can't we?
Yep.
So wasn't the greatest common factor. We'll keep going, and that reduces again to 2/3. All right, so I agree. So, perfect. How about 16/27? What common number goes into both? Nothing. It's already reduced as far as it will go. Okay? And then how about 48/64?
3/4.
That would be, 16, okay? And it gives you 3/4. Now your calculator, just kind of as a backup, you should be able to do it without one for sure, but it does reduce fractions for you. We can check. For example, if you type in 36/54, if I go to alpha y equals, and I say 36 divided by 54, and I press enter, it will all give it to you as a reduced fraction. I want everyone to try that. Make sure you know what I'm talking about. It will reduce it for you. Okay? Try 48/64. Type it in. Alpha y equals, get you that numerator denominator. Press enter, and it will give you the calculator simplifies things for you, which is kind of nice. alpha y equals that n slash d. Taylor, will you turn that light on behind you? It's a little dark in that corner.
Oh, really?
I need my ambiance. All right, better. Okay, now these are simple fractions to reduce and simplify. Those are like, elementary school, middle school fractions. Now that we're in Algebra 2, we're going to be taking these big expressions like this, these rational expressions where I have x's in the numerator and in the denominator, and we're going to simplify them, okay? So, is each of these a rational expression? Well, the one that we know and we like and we've seen a lot of look a little bit like this. Would you agree? Where we had to factor it if we could. We're looking for asymptotes, points of discontinuity, holes, all that kind of stuff. What does this radical in the numerator do? Doesn't it become a radical expression? It messes things up for us a little bit. And then what about this -2? That exponent. What does that do what does that -2 do? Do you remember what that does with the x? Doesn't it need to bring it down here? So isn't this really 3 over positive x squared times x plus 4? Remember that? When you have a negative exponent, don't you put it in the opposite part of the fraction? You should remember that. Okay? And so these are both rational expressions. If you have a negative exponent, like I did in a -2, you just bring it down to make it a +2. That's all. We know how to do that. So let's go ahead and look at something like this. So copy this example into your notes. This is something we have already done before. This helps you on those 9 problems that you had to do, that sheet that I just gave you. This is the same kind of thing. Okay? Can I simplify this? We know how to do it. Aren't we looking for reducing the fraction in the front? And then looking at our exponents and reducing the x's and reducing the y's? I don't see any plus signs. I don't see any minus signs. I don't see any reason to know how to factor. Nothing here. I don't need to factor here. I have no pluses and minuses. I simply just have everything's being multiplied together. So if that is the case, we can reduce it the way it looks. We don't have to factor or do anything special.
Can we like switch things?
Well, we're not going to switch it, but we're definitely going to reduce it. Because 6 goes into 24 and -6, just like the fraction that we just reduced, right? So I can reduce that number. What is 24 divided by -6? -4. Okay? The negative can go in the bottom or the top. I tend to put it out in front. And the 4 should go out in the top, because 24 divided by 6 is 4. Not 1/4, but the 4 goes in the numerator. Now let's go ahead. So we've dealt with the coefficient, the big number. Okay, we've already done this. Now let's look at the x's. Do I have any negative exponents? So I don't need to rearrange any of those values. Okay? Well, I add if they're next to each other, but if they're one on top, what divided by, I don't add, but I subtract. Okay? There'd be how many of them on the top? Good. 3 minus 2 is 1. I have 1x. I have an extra x in the numerator than I do in the denominator, so I have a 4x up there so far.
So y will be at the bottom?
Exactly. So now we're looking at the y values. We know that there's an extra y in the denominator, and so that's the simplified version. We're done.
So we don't have to put that 1?
What 1, baby?
That
You can. You mean like 1 up here and here? What did you mean? Oh, a 1 down. You mean a 1 up front here? You can, but it's not necessary. It wouldn't be wrong to do that, but it's not necessary. Okay? I actually just like it just like this. So that is the simplified version. And remember we did a little half sheet like a month or so ago. Christian's working on it now. Okay? So that's what that's what you had to do, this kind of stuff. Okay. That's easy. That's review. We got that. We know what we're doing. It's when the problem becomes something like this that gets a little bit more complicated. Okay? So here's a second example to put in your notes. Come on. You got it.
You do it?
Yep. It's not any different than what you were doing a minute ago on your OPQ. Those of you who had to factor. There were several OPQs you didn't have to factor, by the way. Why would factoring be a good idea here? What tells us, why is this one different than the one we just looked at? What tells us to factor here, Moody? Moody? Not, okay, the degree is helpful, I agree, but why factor, Christian? I have a trinomial, good. I've got a plus and a minus sign in the numerator, and I have the same thing in the denominator. It is a quadratic trinomial, which means I am going to factor. Okay? So we're going to factor both the numerator and the denominator. We're going to factor them both. Factor the numerator and the denominator. Two numbers that multiply to be negative 8 and add to be 2. What are they?
4.
4 and negative 2. So x plus 4, x minus 2. Right? It's two numbers that multiply to be the numerator. I'm sorry, two numbers that multiply to be the last number and add to be the middle number. I also need to factor the denominator. So I'm just going to kind of do a little erasing here. We want two numbers that multiply to be 6 and add to be negative 5.
6 and a negative 1.
Good, a positive, no, not a negative 6 and a positive 1. Good. That doesn't work. That negative 6 and positive 1 gives you a negative 6 here. So that doesn't work.
2 and 3.
Okay, good. So this one always, we think, because 5 and 1, we think it should work, but it doesn't actually. So once we have positive 6 and then we add to be negative 5. So it should be a negative 2 and a negative 3, right? Because they multiply to be a positive 6 and then they add to be a negative 5. So x minus 2 and x minus 3. Okay? Just factoring. All I did. Right, Christian? Just looking at factoring the numerator and the denominator, just like your OPQ. Okay? Now, if there is a common factor in the numerator and the denominator, we're going to just cancel it, just like we did before. It's kind of like there's a hole there, right? Isn't that what we do in the graph? There's a hole in the graph there. So that's exactly the same thing that we've already done. We know how to do this. It's nothing new, Joseph. Put your phone away.
So it's going to be x plus 4 over x minus 3.
You want to teach? Let's go. I know, it's not broken. I do it all the time. All right, I'm good. All right, so we're going to cancel out our common factor. There's a hole in the graph when x minus 2 equals 0. I agree. And what is left, as Tim said, is just what's left. X plus 4 over x minus 3. Done. Yes. It's not hard. There is something that we need to just talk about. That is the answer that is simplified. Okay? We're just looking, it's going to ask you what are domain restrictions. Well, shoot, we talked about that this morning with the graph. We already know. What are the restrictions? X can't be 2, and x can't be positive 2, and x can't be 3. Turn up.
Turn up.
Turn up.
Happy lunch. I just now remember.
Pie in the face. I'm not picking you to put the pie in my face because you'll like. All right, so x can't be 2 because of the hole. So a domain restriction, any restriction, x can't be 2 and x can't be 3. It's where those holes and vertical asymptotes are. We know this. Come on, Miss Mackert. Make it hard. It's not hard. We got it. All right, here we go. Here's another one. Okay? I just want you to simplify it. Okay? I just want you to simplify it.
Oh,
Uh-huh. I want you to factor the top. Look at the second question, or question number 9. When I'm trying to factor the top,
We gotta factor that?
always. Is there a GCF?
It's not x squared.
There's no x squared, but there's a GCF. What is it?
4.
4, or is it negative 4?
Negative 4.
Well, I don't, it could be either.
It's 4
So-
because it's not a negative 4.
Okay, so hang on. Let's do it your way from, I'm going to do 2 ways. Okay? If I take a 4 out, I'm going to have a 3 minus x. I agree. If I took a negative 4 out, wouldn't I have, what would I have? Negative 3 plus x. Isn't that the same thing as x minus 3? Okay, so we have 2 options. Which one is the better option? Well, I'm not sure yet. And it's actually the second one. I'm going to tell you why. Okay? This is actually the same thing as this. I'm going to tell you why that one's better. Because don't I have to factor the bottom too? All right, so when I factor the bottom, what are the 2 factors down there? X plus 3 and x minus 3. Okay? So if I say x plus 3 and x minus 3. So we're looking at these 2 options here. Which one looks better to you? The first one on the left or the second one on the right? Why, Daniel? You're right. Now I have a common factor that cancels. But not really, because there's a negative out there. Okay? These are not the same. I'm going to highlight them. These are not the same factors, because the negative goes with the x in the top and the negative goes with the 3 in the bottom. So they look similar, but because of this negative that I took out, now I have a common factor that will cancel. Okay? So we have to be pretty careful when we're factoring. We want the factors to look exactly alike. They looked close over here on the left, so that is your hint. If they look close, then I should probably have taken out a negative here. Okay? I took out a negative 4 because I wanted the factors to look exactly alike.
So we gotta cross the other one out.
Yeah, this is still correct, but it's not simplified. So to correctly simplify, you want the factors to look identical, which means that sometimes you have to take out a negative value. Okay? And that's okay. So we're not going to do it this way. In this case, just in this case. So when I'm done with canceling my common factor, isn't this the final answer? I have a negative 4 left in the numerator, and I have an x plus 3 left in the denominator. Okay? Good. All right. Ready to try another one?
Yeah.
Okay. Oh, hang on.
Oh, that's homework.
So,
You have to do the homework type stuff.
now, I'm going to just have, all we're going to do is multiply, and then we're going to stop. We're not going to move on to division yet. So this is like the hardest one you would do.
So we got
Okay.
time? Oh, wait.
So hang on. So what's different about this one than just plain old simplifying? Okay, so that you hold that thought. There's a couple of steps. One, I got to factor, and then I have to factor a bunch of stuff. I got to factor 4 times. 4 times. You better become factoring pros by the end of this week.
But the top left one, you can't factor.
Yes, you can. There's a GCF of a 2 in there.
But what is the x squared?
Doesn't matter. You don't have to have an x squared to always factor. It can just be a GCF. Now, Tim said, do I cross multiply? The only time I cross multiply is when I have an equation where I have an equal sign in the middle, and I don't have that here. So I'm not going to cross multiply. I'm just going to look for things to cancel and reduce. Okay? If there's something on the top that is the same as something on the bottom. Honestly, when there's a multiply sign here, once I have everything factored, I can just put one long fraction bar across the top. Okay? Multiply, you just multiply straight across. So it doesn't really affect anything.
Like we usually do.
Yeah. So right now, I just want you to factor this. I'm going to pause the recording, put attendance in. I want you guys to factor 4 times, both the top and the bottom of the left hand and the top and the bottom on the right hand side. Okay, numerator, denominator for both. Factor everything. All right, ready? Let's go. Let's factor both the numerator and the denominator. Okay? You should have factored it to be a 2 in the numerator, a GCF of 2. You're left with an x minus 4 on the top left. You get that? It's factored out of 2. The denominator, x squared minus 16, is just x plus 4, x minus 4. It's a difference of perfect squares there in the denominator on the first part. On the right-hand side, the two numbers that multiply to be 4 and add to be 5 are 4 and 1. X plus 4, x plus 1. And in the denominator, you have 4 and 4. So x plus 4, x plus 4. When you multiply fractions, you just multiply straight across. So quite frankly, I can just make one big old fraction bar. It doesn't matter. Okay? And I'm literally looking for common factors in the numerator and the denominator to cancel. I'm looking for kind of like holes in the graph, so to speak. So where are those going to be? Well, I have an x plus 4 here and here, but only one of them's canceled. And then on the left-hand side, I have an x minus 4 and an x minus 4 that cancel. Do you agree? The 2 doesn't cancel with anything. Okay, and this other stuff. There's a whole bunch left. Okay? So honestly, what's left, we're going to rewrite it with whatever's left. So I still have a 2 up there. Yep. And I also have an x plus 1 up there. Do you agree? Whatever's left in the numerator stays there. What's left in the denominator is 2 of the x plus 4s. Now, I can write it twice, or I can write it like that. Either way. I'm not going to be picky. There's 2 of them. Right? It doesn't matter if you write it twice. I'm okay with that. But I'm just showing you a different way to write your answer. No big deal. Now, what are the restrictions? What can't x be? So x can't be positive 4 because it canceled out with over here on the factor. It can't be negative 4, and that's also what's in the bottom. So the 2 domain restrictions we would write like this. X can't be positive or negative 4 because that's where the holes and the asymptotes are. We good? That's all you have to do. That's all you have to write. Right, Ro? It's not any harder than what, actually, I think graphing it was harder because you had to do this and more. Right?
For the x plus 4 squared, couldn't you just write that as like x squared plus 8? No,
because it would be x squared. It would be x squared plus 8x plus 16 because you have to FOIL it. This whole thing over here is the answer. Yeah, it doesn't really matter. Yeah, comma, whatever. That's a domain restriction that I wrote here. So you have to kind of include that with your answer. Okay, what you do. I want you to include your restrictions in your answer. Okay? All right.
Why is it only 4?
It's plus or minus 4. Both of them, positive and negative. I just wrote it together. You can write them separate if you want. X can't be positive 4, X can't be negative 4. Right, that's just the domain restrictions. Whatever canceled and what's still left in the denominator. All right, let me go ahead and assign you what your homework is. Okay? Only simplifying and multiplying. We'll get to dividing next week. So on page 531 of your textbook, I'm going to have you guys do 8 through 18 even. It's really 6 problems. It's not that many. Okay? So 6 problems. I think you can do it. Don't you? Yeah. All right.